Hello and welcome to 19th lecture in the 19th chapter of our comprehensive course on AI, ML and DS. Now here we want to discuss practical applications of central limit theorem, and we want to discuss 5 applications one by one. One is this confidence interval construction. Second is hypothesis testing. Third is quality control in manufacturing. Fourth is data sampling in surveys. And fifth is algorithm performance evaluation. So now if I read all this, then at least after so many chapters, you will find that none of the term or none of the word will look strange or unfamiliar to your ears. So confidence interval construction. For example, in a customer analytics project, we want to estimate average monthly spending of customers with a certain confidence level. So that means, suppose you want to decide that what will be the revenue of your streaming platform. Suppose you are the in charge of some Netflix or that kind of streaming platform, and you want to estimate what kind of revenue you can expect in the coming months. You already know the total number of subscribers or the customers, right? That you have suppose total 0.1 million or 1 million subscribers. And now you want to estimate that how much monthly amount will they spend on additional purchases, on new movies, new documentaries or something apart from their regular subscription, right? So in that case, and that you want to get with say around 95% confidence interval. Now suppose you get the answer that average monthly spending of customer is going to be $5, additional spending apart from their subscription charge is $5 plus or minus 90% of $5. Okay, so that means actual can be $5 minus plus or minus 90% is wrong, plus or minus 10%. So that is called 90% confidence interval, right? So it is $5 minus 10% of $5, that is $0.5. So maybe 4.95 to $5 plus 10% of $5, so that is 5.5. So you want to decide that thing, that average spending of each customer will be between 4.95 to $5.95, and then you just have to multiply by number of customers. That will give you a fair idea about what revenue you can expect from the streaming platform, right? Similarly, hypothesis testing. For example, you want to do that A/B testing of two different versions of same website, and you want mean click-through rate for the two website designs A and B. Then quality control in manufacturing. For example, a factory produces metal rods, and you want to ensure that the rod length stays within some acceptable limit. So suppose the rod length has to be exactly say 25 centimeter plus or minus 1 millimeter. So that much margin of error is allowed. Otherwise, it is to be used in some precision machinery, and more than that margin of error is not allowed. So you are doing that quality control. Then data sampling in surveys. Suppose you are doing a simple survey in a city to estimate what proportion of city's population prefer one specific brand of coffee. Okay, or algorithm performance evaluation. For example, in machine learning project, you want to evaluate a model's performance using k-fold cross validation. So in previous lecture, we have seen that k-fold cross validation is like this. So you want to evaluate the performance of the model, right? Now in all these cases, all these 5 applications, whatever we have discussed, central limit theorem is the key pillar. Without central limit theorem, you could not do the process that we are going to describe. So let us take each application one by one in detail. First, confidence interval construction. So in a customer analytics project, you want to estimate the average monthly spending of customers. Now, how central limit theorem helps? Then by taking some random sample of customers and calculating their mean spending, the central limit theorem allows to estimate the sampling distribution of the mean. Now, what is the meaning of this sentence? Then as I have said many times, that the entire art of statistics or machine learning, hypothesis building and machine learning also, inferential statistics, is to get the parameters, statistical parameters related to population, which are otherwise very difficult to obtain because the population is very large, diverse, and so many issues are there. So to get the statistical parameters related with population by using by estimating the same statistical parameter for sample. For example, this is the diverse population of say 2 million customers of Walmart, and you are asked what is the population mean X bar. Now I cannot estimate it directly, but I can take small samples and I can find the mean of all samples, and I can plot a graph like this. Then we have seen that all sample means they follow a Gaussian distribution, and once they follow this kind of Gaussian distribution, thereafter you can find the mean of the population from the mean of any one sample, or maybe by taking average of the means of all these sample or whatever, that is whatever is the mean of this normal distribution, that you can take as a population mean, right? So that is what is written by taking some random sample of now customers. So here suppose this is that customers and calculating their mean spending. So CLT, central limit theorem, allows to estimate the sampling distribution of the mean. Okay, so first we estimate sample mean like this. This is the sampling distribution of mean, this red colored graph, that is the where my cursor is just above this my image in, which is in the video. So that my cursor, you can see this red color graph is normal distribution. So I will estimate a sample mean, and from sample mean I will say that the population mean is this much. Okay, and their concept of this confidence interval comes that okay, central limit theorem says that sample mean is almost gives a fair idea of population mean, but fair idea does not mean that population mean which I am interested in is the same as sample mean. There would be some small variation. So then the next question would be what is the maximum applicable variation? So if I entertain the symbol, because here the symbols are interchanged, that is why, no other specific reason. So let us call this sample mean as mu, okay, and this not mu, sorry, sample mean as x bar, and population mean as mu, because that is how it is explained here. That is the reason. So population mean which I want to estimate is suppose mu, but I am trying to use central limit theorem, and which guarantees that if I get the sample mean, then that will be a fairly close estimate of population mean. But fairly close means there will be some margin of error. So the question is, what is the margin of error? The answer to that question is given by confidence interval. It says that the population mean would be equal to sample mean, that is x bar, plus or minus z score into standard deviation divided by the number of observations in the sample, which is also called standard error. This ratio sigma divided by root m, that is also called standard error. So z score corresponding to desired confidence level. So now there, what is the meaning? Suppose someone says that I want to estimate this parameter, that is population mean, from this parameter, that is sample mean, with 95% confidence interval. So then you will have to find the z value, z score, corresponding to 95% confidence interval. Okay, and for that there are ready-made tables. For example, here only you can see 95%, then the value of z is 1.96. So what you will put here, that whatever the value of this sample mean is there, x bar, plus or minus 1.96 multiplied by the standard deviation of the sample divided by the number of observations in the sample in the root. Okay, that means standard error is this much. So then suppose this answer 1.96 multiplied by sigma divided by root n, that comes out to be say 0.35, and suppose this sample mean that came out to be 45.65, while what is that standard error? That standard error is this whole thing, that is z into sigma divided by root n. Standard error multiplied by z is equal to 1.96. That whole thing comes out to be suppose plus or minus 0.35, right? So in that case, I will say that if my sample mean is 45.65, then my population mean will be very close, but there might be some change. How much change? 45.65 minus 0.35. So that will be 45.30 and 45.65 plus 0.35. Now that would be 5, so 70 and 30. So that would be 46. So I would say that if I get a sample mean of 45.65 and if the confidence interval is 95%, then in that case my population will vary between in this interval 45.30 to 46, and I can say with 95% confidence that the population mean will be found in this interval only. That is the meaning of confidence interval. So let us do some more discussion. What is confidence interval? Now, most important use of confidence interval is in market research. So market research is an important part of inferential statistics. So as I said, when you discuss the central limit theorem, at that time you have already entered into the inferential statistic from descriptive statistic, right? So market research is an important part of inferential statistics, and most market research is done based on the concept of confidence interval. Let us take one example. First, what is a confidence interval? A confidence interval is the range of value which the researcher can be fairly certain that their true value of interest lies in. What is the meaning? Here, I was not at all interested in my sample. I was interested in getting statistics related with my population. So that means I was interested in finding this parameter, that is population mean. But unfortunately, my population is very large, maybe 2 million of customer observations, and it is so diverse that finding the mean of that population is not feasible. Okay, so in that case, what I do is I take the help of central limit theorem, that I take sufficiently independent and large number of samples. Each sample should be having more than 30 observations, and these samples should not be interacting with each other, right? So in that case, I can find the mean of that sample. So that I got this value, suppose 45.65. For sample mean finding is very easy, because the minimum size of the sample is 30. So normally 5,000 here I have written, but mostly around 550 sample is also considered good enough. So if I find whatever parameters, say customer spending I am estimating, then customer spending of 50 customers is known to me from this sample, then I will just add them and divide by 50. That will give me the mean value, and then I will find the standard deviation in that and divide it by root 50, because n is equal to 50. So then, and multiply by 1.96, because 1.96 is the Z score corresponding to 95% of the confidence interval. And suppose that gave me this 0.35. So I can easily say that this value which I am interested in I am fairly certain with 95% confidence that it will fall in between this range. Now if you read this again, then it becomes clear. A confidence interval is the range of value which the researcher can be fairly certain of that their true value of interest, this is my true value of interest, population mean, will lie in. So I can be fairly certain with 95% confidence that my population mean will lie from 45.30 to 46. Okay. For example, in the purpose of taking a random sample from population of interest and computing some statistics such as mean, here mean is calculated, but you can calculate any statistics. Suppose someone says find variance of the population. Again, we do the same thing. We don't find variance of population, we find variance of the sample, and from that we say that using central limit theorem, variance of the sample gives a fair idea of the variance of the population, like that. Okay, but again that will be subject to certain plus or minus or confidence interval, right? So the purpose of taking random sample from a population of interest and computing any statistics such as mean, variance, etc. from the simple data is to determine an approximate estimate of the mean of the greater population. However, the researcher must also be wary of how well the simple statistic actually estimates the underlying population value, because as I said that this is not the case that this is exactly the same as this sample mean is exactly the same as the population mean. Some range of inaccuracy will always come. Okay, so confidence interval addresses this concern that, okay, population mean is not exactly the sample mean, fine, but at least I can give a range and I can tell that with this much confidence, I can say maybe that is 95% confidence or 90% confidence, that is another matter, but with this much confidence, I can say that my population mean will be in this region only, right? Okay, now what is confidence level? Then all confidence intervals are constructed using some confidence level, because here you have to put the value of Z, right? So if it is 95% confidence level, then in that case you will put Z is equal to 1.96. Now for this Z, there is some ready-made table only, and this kind of table is there. So if you want to find what is the value of Z for 0.95% confidence interval and all that, then you have to look at this table in reverse direction, and wherever you find 0.95, okay, from that you have to find the corresponding value of Z. But that is another matter. I will teach you how to see this table. But currently we are just interested in this many value of Z. Okay, so you can see that instead of 95%, if I want to use 90%, then instead of 1.96, I will have to use Z is equal to 1.645, right? So all confidence intervals are constructed at some confidence level. For instance, 95% or 90% or 99% or so on. Then the confidence level is selected by researchers who are conducting the statistical analysis. So let us say I have selected 95% confidence interval, or that means I have selected that Z is equal to 1.96. Okay, now in that case, suppose what is the exact meaning of that 95% confidence interval? It means that if the same population were to be sampled on multiple occasions and estimation of parameter means here mean for example, were made on each occasion, then the resulting interval would include the true population parameter in approximately 95% of the cases. What is the meaning of this sentence? Please understand. Okay, so this mean sample mean 45.65 I got by taking sample once, but similar samples you have to take again. So this time, next time, suppose take some different samples here, again find the mean of each sample and again see their plot their distribution. Then again sample means will be distributed along Gaussian curve and bell curve, and then you can find the mean of that. That would become the new sample mean for the second trial while taking totally different samples than what are shown in this figure, right? And that sample mean will give me some value of some estimation of population mean. But howsoever large number of experiments I do, this range says that my actual value of interest, that is this value, population mean, will fall in this range with 95% of the cases. So if I draw such samples 100 times, then in 95% of the cases, my population mean will fall in this interval only. That is the meaning of 95% confidence interval. Similarly, if it is written 99% confidence interval, then in that case, if I draw the samples 100 times, same experiment of drawing one sample, estimating their mean, finding the Z score, finding the standard deviation, and finding this standard error and this whole plus or minus term, same thing, you do 100 times. Then if confidence interval is 99%, then I would say that my value of population mean will fall in this some particular range with in 99 out of 100 experiments. Okay, that is the meaning of that. However, at that time range would be different because this was the range for 95% confidence interval, and for 95% confidence interval I had used Z is equal to 1.96. For 99% confidence interval I would use 2.576. So in short, this Z has increased, this Z here, and therefore the plus or minus range would also increase, right? So that is about that confidence interval. Now let us take one example, how to calculate confidence interval step by step mathematically by our hand, not by program but by our hand. Okay, so in that case what I will do is, suppose you are a group of researchers who are working for a large grocery chain which has branches all over US, and your grocery chain wants to supply oranges to your customers, and you have decided that all oranges must be of certain minimum size. By size here is the certain minimum weight. Okay, now you are tasked with that. So that means what you will do, you will go to visit various farms or the owners of the orchards, and you will, now each orchard will have thousands and thousands of oranges. So will you go and pick up each orange and measure each orange and measure its weight? Because if you do that, that is completely infeasible, and that, then what is the use of all this central limit theorem and statistical knowledge, and what is the use of hiring a group of researchers, right? So the group of researchers who are trained statisticians, they will do it like this. They will just randomly select 46. Now 46 is just an example. Instead of 46, it can be any number. Okay, let us take a different number. Suppose they will randomly select maybe 50, right? So 50 oranges from the trees on the farm, and they will take care that they, when they select the sample, at that time they will take representative sample. So they will not pick up all 50 oranges from one tree only. Suppose this is a big orchard, then they will take one from here, one from here, one from somewhere here, one from somewhere here, so that the samples are independent and truly representative of the population. Okay, so they have taken 50 oranges, and suppose they find that the mean weight of the orange is 86 gram. Okay, so that means it is clear that x bar is equal to 86 gram. That is sample mean is equal to 86 gram. This x bar, right? Sample mean, correct? Now they also calculate the standard deviation, because you have not measured the weight of one orange. You have measured the weight of 50 oranges. So that means it would be like this, that number 1, 2, 3, and so on up to 50, and weights are, say, sometimes it will not be exactly how much is the average. Mean is the mean is 86, right? So sometimes they will get maybe 84, sometimes they will get maybe 89, sometimes it would be 85, and so on up to, suppose this last observation is 83. But the sum of these observations when I take and divide by n, number of observation, so that is sigma xi, where I varies from 1 to 50, that I am not writing, divided by 50, because here the number of observation is 50. That will give me x bar, that is sample mean. And suppose that sample mean comes out to be, that is 86 gram. Okay. Now how to find the standard deviation and variance, that also we know. Here we make another table in which we find each weight, w minus w mean. Okay. So w minus x bar. So 84 minus 86, this comes out to be, sample mean comes out to be 86 gram. So mean weight of the sample, orange sample, comes out to be 86 gram. Then you do 84 minus 86, so that is minus 2. Then 89 minus 86, so that is plus 3. 85 minus 86, so that is minus 1, and so on up to 83 minus 86, so minus 3. But these are some positive, some negative, so we do one thing. This is like xi minus x bar, right? So xi minus x bar, so we do the square of it, and then we do sigma xi minus x bar whole square, or here sigma w minus x bar whole square, right? So weight of each minus x bar whole square, and that divided by n, that gives me, or n minus 1 for sample, that gives me the variance, or that gives me sigma square. And Suppose from that, if I find square root, then I will get sigma. And suppose the sigma comes out to be here 6.2 grams. Here instead of sigma, the symbol which they have used for this example is S. So then S comes out to be 6.2 gram. That is sample standard deviation. Okay. So I can easily find the Z value first for confidence interval, because suppose my researchers are asked that you select appropriate confidence interval so that each and every orange which is coming to our grocery chain should be having weight uh, around 85 gram within that confidence interval, right? So then as a researcher, you can select that 95% is more than enough, because this is not some life and death kind of issue like medical diagnosis or cancer diagnosis where 99% confidence interval is required. So 95% seems to be good enough. Confidence level seems to be good enough. So you take Z is equal to 95, for which this is 1.96, right? So as a result, you have found now Z score. So you can use that formula, this formula, for calculating the confidence interval. That it is X bar plus or minus Z multiplied by sigma, that is the standard deviation of the sample. Here it is shown by S, and divided by root n. So then in this case, X bar is 86 plus or minus sigma. Sigma is, sorry, plus or minus Z. Z is 1 for 95% confidence interval. It is 1.96 from the table on the left side, and multiplied by standard deviation, which is 6.2, divided by root of 50, right? Now whatever is this value, that value will be the confidence interval, right? And here, if you find it, this is not root of 50, that is root of, I think, first, because we have taken some different number of observation, no, 46 or something. So root of 50, if I calculate, that is 5 root 2, or 5 multiplied by 1.414, or that is 7.07. That is the value of root 50. Let us check just, but I think it is correct. So 50 and root, so 7.07, right? So that is the value of root 50. And if I calculate 1.96 into this also, then in that case, 6.2 divided by 7.07, sorry, is equal to 0.87, okay, multiplied by 1.96. That is the value of the Z score corresponding to 95% confidence interval. Here I can write minus sign and then plus 86. So that will give me the lower range value 84.28. Okay, so 84.28 here, 28. And higher value if I want to find, then that would be if I do this only again and then minus, and then not minus, sorry, but this time I want to add it to 86 gram, right? So 86 plus this, so 87.71, okay, so or 72. So this is the range that I am getting. Now what is the meaning of this whole thing? If I do that, then I am, suppose, the leader of that team, and I have to visit maybe 5,000 orchards spread over entire United States, and I am given a simple task that you have to ensure that each and every orange comes out to be within this range, that is 86 gram minimum size, maybe plus or minus this much, 1.79 would be allowed, but not more than that. So that means 84.28 gram is the minimum value allowed, and 87.72 gram is the maximum value allowed. And you should do your job with 95% confidence level. Now what is the meaning? That means if 100 oranges come from the orchards all over the United States, then out of them at least 95 or more oranges should be having weight in this region. Say out of 100, if 5 are underweight or overweight, that is fine, but I am the quality control in charge, so I have to ensure that out of 100, 95 have weight in this region. So how I started, if you now do step by step quickly, then select a sample of 50 oranges, right? Then selected a sample of 50 oranges, measured weight of 50 oranges, found their mean weight, then subtracted each weight from its mean value, and found the square divided by n minus 1, that gave me variance, and find its square root of whole term, that gave me standard deviation. So I found that my mean is 86 grams, suppose, and I want to find 95% confidence interval. So this is the value of Z corresponding to 95% confidence interval, right? Okay, so this is the value of Z, and this is sigma divided by root n. So if I find that, then I found that the standard deviation is 6.2, and this range came out to be 86 plus or minus 1.96 multiplied by 6.2 divided by root of 50. This is the value of root of 50, and therefore if I found, ultimately I got that it is 84.282. Confidence interval is shown in this manner by a kind of close interval in mathematics, right? So 87.72. Now what is the conclusion? That I have said that I have ensured, if I just, now how will I ensure that all my oranges fall in this range only, from where all out of hundreds and millions of oranges they will fall in this weight only? Will I go to each orchard, thousands of orchards, and will I measure the weight of each and every orange? No. I will go to each orchard and just take a sample of 50 oranges from each orchard and just find their mean and standard deviation. And if I have decided this confidence interval, then I can be fairly sure that if the mean came out to be 86 and the standard deviation of the sample came out to be this much, then I can be, with for a sample size of 50, then I can be fairly sure that out of every 100 oranges, 95 oranges will be falling in this region. That is the meaning of 95% confidence interval, right? Now, we can do the same thing programmatically. So here, let us say I take a random seed, and here I take a gamma population, because that is what is the essence of central limit theorem, right? That original population does not require to be normal. So you can have a normal population or non-normal population or any kind of population, but when you take multiple samples and find the distribution of means, so this is exponential, this was uniform, this was bell curve, but from all, when you take multiple samples and plot the sample means, then the sample means will always follow the Gaussian distribution or the normal distribution or the bell curve, right? That is the essence of central limit theorem. So this time I choose some another np.random.gamma. We have done many np.random.normal, np.random.uniform, np.random.exponential, np.random. I think still one more is there somewhere earlier, much earlier. One last example which we have done. So all these different kinds of population, yeah, normal, binomial, np.random.Poisson, np.random.logarithmic, many different types. So this time we take gamma distribution and np.random.gamma. So suppose my orange population all over country is found to be changing according to this, and suppose I take sample size of 30 and number of samples is equal to 50. Now I initiate two empty lists, one for means and another for intervals, right? And then I use a for loop symbol to populate these means and my intervals, and thereafter I keep on appending to this list one by one. And here this is that formula, that is 1.96, which is the z-score, multiplied by the standard deviation of the sample, and which is found by np dot standard deviation, right? Okay, divided by np dot square root, that is under the root, sample size. Sample size is here 30. That is this formula, that is here. So sample mean plus z for 95% confidence interval, z is equal to 1.96 into standard deviation of the sample, np dot standard, and divided by square root of number of observations. So if I find that, I will get the confidence interval, right? And then I can append the values, but this time I will append with confidence interval. So if I append that and find it and plot the diagram, right? So if you do that, ultimately you get this kind of diagram. That confidence intervals for the sample means are this. Here, what is the sample mean? If you find, I can plot one or two more extra line here, maybe where the function is called. Okay, so function is not defined, but directly only the for loop is defined. So I can write one extra line here, print sample mean, and that also should be printed out of the for loop, right? Because there is no point in printing every sample mean, and or print means and print intervals. Because then only you will be able to understand what we got in the graph. So these are the means, okay? 3.96, 3.10, 4.45, and so on. So here somewhere, if you see, this is 4 point something. The first mean is 3.96, just slightly less than 4. This is 3.10, far less than 4. So you can see it is far less than 4, 3.10, right? Then the next mean is 4.45, so it is above 4. This red colored line is the 4. So it is above 4, and so on, right? But I can ultimately find, these are the means for each samples. How many samples I have taken? 50. So I am finding the means for each sample. So they are distributed in this manner, and then I find the mean of all means. Okay, and that comes out to be 4, I think, right? So that is this dotted line, or red colored dotted line. So that is called true mean. And similarly, sample standard deviation, if I here add one line for clarity, then okay, so these are the standard deviation. So 3.96 plus or minus 3.23, but that standard deviation would be divided by no, these are intervals, right? So intervals means I think I should okay, no problem, fine. So that is where is that interval calculated? Interval dot append is equal to, yeah. So these are the values directly of sample mean minus confidence interval and sample mean plus confidence interval. That is interval. That is, it is like this: 86 plus this term and 86 minus this term. Where what is this term that we know? This is z value. This is sigma standard deviation, and this is the root of number of observation. So exactly same thing. You are calculating that confidence interval. This is the z value corresponding to 95% confidence interval. This is the standard deviation. This is the root of sample size. And if you find it, then those intervals will become plus or minus. So this is sample mean minus confidence interval and sample mean plus confidence interval. So these are intervals. Now if I even print that CI, then it will become clear even more. Okay. So maybe print CI. Now CI will be, okay, I think it will be only one value. Yeah. So confidence intervals are this. Again, I can put one line here for better separation. So yes, this is the confidence interval, right? So if this is the sample mean, then plus or minus this much value, that gives me this interval, first interval. Similarly, if this is the sample mean, then plus or minus this value, that gives me the other confidence interval. Similarly, if this is the sample mean, then plus or minus this value, that gives me the other confidence interval, and so on, right? And therefore, my final mean would be equal to this true mean plus or minus this confidence interval, right? So that would be 4 plus or minus 1.3957. So that is 4 minus 1.3957 and 4 plus 1.3957. That will be the mean of population, because as such I was calculating various sample means, but never forget what is your purpose. Your purpose is to calculate quantity for sample, but from that you want to estimate quantity for population, and their confidence interval comes into picture. So I found that my population mean is 4 plus or minus this with a confidence of 95%. That is in 100 out of 95 out of 100 new samples if I will take, then I'm sure that population mean will still come out to be this only. Okay, that is the meaning of confidence interval, right? And this distribution also you can check that it would be nearly Gaussian. Here some intermediate values are not there. That is why it is not looking very correctly, but it is Gaussian because the sample means are always distributed in a Gaussian distribution manner, irrespective of what was the original population mean. Original population was gamma distribution, but that does not matter. Sample means are always distributed according to bell curve, right? So that is what you are getting here. Now next example, we will take a second example of second use of this central limit theorem, that is in the hypothesis testing. So see you at that time, and just hang on.